Thank you. Please remind me the next time as well. No time dependence. And in no heat generation, we can say that we can neglect the E dot gen term. So just like in very, very brief, in like 30 seconds, I'm just going to uh, revise all the things which we covered here because I didn't start the recording, my bad. We covered the first law of thermodynamics, in which we showed that change in the energy of any system is dependent on how much energy goes in and how much energy comes out. Then there is heat conduction, in which we discussed the conductive heat transfer, convective, and the radiative. And the form, I think I forgot the convection heat transfer formula. It is, oh, Q dot convection is essentially H times A times delta T. What is this? We'll come to this in some problems which we will discuss. So good that we revise this. Anyways, radiative, this is the formula. And then we came to week two, in which we are discussing what is the 3D form of the Fourier's law. And assuming steady state and no heat generation, we can neglect the two terms, this term and this term. So what comes to us is in 3D with these two assumptions, these two assumptions, we will have d square t over dx square equals 0. I mean, this is the usual Fourier's law, assuming that there is steady state and there is no heat generation. If we have the same thing but in spherical coordinates, because we will have problems which will have spherical coordinates, it simply becomes r times d square t over dr square plus 2 times dt over dr equals 0. And for the cylindrical coordinates, it is d by dr of r times dt over dr. If none of what I am discussing right now is making sense to you, it is all right. These are just simple formulas which you essentially won't even have to remember. Uh, you'll get the hang of all this once we'll be discussing the problems. So how to apply this is more important rather than just going through the formulas. Okay, so the general formula for the the most general way of writing the heat conductive formula, most general form would be, I mean, in this we are no assuming no steady state. Okay, the previous assumptions we are neglecting now, and heat generation is also there. Okay, so the most general form of heat transfer equation would be 1 over r to the power n times dou over dou r to the power n k times dou t over dou r plus E dot gen equals rho cp dou t over dou t. Okay, again you don't have to remember this. Now in this, what is n? N is 0 for the 3D case, n is 1 for the cylindrical case, and n is 2 for the spherical case. Okay, so this is essentially, I've just covered the theory of week 1 and week 2 in very, very brief. Now I think we'll directly come to the questions, and I think let's begin. I am pulling out the questions. Give me a sec. I hope you all also have the questions. It's there in the Teams group, which I have um, created. Okay. So let's begin with the first problem which I've shared, which is problem 1-35. All these problems I've taken from the book Incropera. Incropera is the name of the author. The textbook I think which you guys have is Sengil and Eunice. Um, but this Incropera is the one from which previously uh, the prof took out the questions for the like CAs or even the like the midsims or the exams. So I just thought I'll just pull up questions from here so that you can have more diverse set of questions to practice from. And if you have any queries, we can discuss right now or later. Okay. Just for a check, I hope I'm still audible and everything is fine. Okay. Someone just give me a thumbs up, maybe. Okay, thank you. Thank you, Ganesh. Mm. So problem 135, which states that uh, we have a system in which there is, oh, why is this not working? Hmm. We have a system, okay. In this system, we have one iron block and one aluminum block, okay. Each one has their own specifications. The iron block is 20 kgs, and this one is also 20 kgs. Then this one is at 100 degrees Celsius. This one is at 200 degrees Celsius. And we have the specific heats of both the things as well. So specific heats would be CP. So CP of iron is 0.45 kilojoule per kg degree Celsius, and CP of aluminum is given as 0.973 kilojoule per kg degree Celsius or kg Kelvin. Anything is fine. Um, Usually, the specific heats are dependent on temperature, but in general, they don't vary much with like smaller changes in temperature. So that's why we can take them as constant. Ideally, we should be integrating. Um, Now, this is the situation at t is equal to 0. Okay? T equals 0. This is the situation. What they're asking is after t is equal to infinity, whenever we reach equilibrium, what will be the state? Same box, same iron and aluminum. Now, what is going to be the state after equilibrium is reached? Okay. I'll give you guys like 1 minute to think and then I'll begin the solution. Very, very simple problem. No need to think of conduction, radiation, convection. It is simply energy balance equation and that's it. Okay, so let's begin. Um, let's call mm, this outer boundary, this thing, as our system, okay? This is our system. Does this or any? I mean, inside this, there is the presence of iron, there is the presence of aluminum, but the system itself, it has no thickness, right? It is just a layer. So it essentially has no volume, no mass. It does not contain any energy. So simply applying the first law of thermodynamics, we have um E in minus out equals of this. And what is delta in system? It is zero because system has no volume. So essentially what we are saying is, and no, it is going out as well. E dot okay. I think I got disconnected. Anyways, so this is valid at t is equal to 0 as well as t equals infinity. So what I'm trying to say is that we can simply say that let's assume at t is equal to 0, the iron was at a temperature, how much was it? Let's call it TFE, which is I think 100 degrees. Okay, yes, 100 degrees Celsius. And the aluminum was at TAL, which is 200 degrees Celsius. What happened at T is equal to infinity? Both of them are going to come at the same temperature, right? They will exchange heats from whichever to whichever, but essentially they will come to the same um, temperature, which let's call it T2. Okay, so iron would be at a temperature T2 and aluminum also would be at a temperature T2, right? So using this equation E in equals 0, we can simply say that m dot Cp times delta T of iron plus m dot Cp times delta T of aluminum. This is also aluminum. Oh, sorry, this is iron. This is Fe equals 0. This makes sense. It's just saying that there is no heat transfer which is taking from inside the system to the outside the system. So whatever change of temperature, whatever heat transfer happens in the iron, which is m dot Cp delta Tfe, and whatever heat transfer happens in aluminum, if we add both of them, it should essentially be zero, right? So we just have to simply plug in the values now. What is m dot of iron? I think it's 20 kgs, right? Okay. So 20 times what is Cp of iron? Cp of iron is 0.45, but please notice that it is kilojoule. So we have to multiply that by 1000 to come to SI units. And then what is delta T of Fe? What is the change in temperature which happened in the iron? It is very simply the final temperature of iron minus the initial temperature of iron. What is the final temperature of iron? It is T2, right? And what was the initial temperature of iron? 100 degrees Celsius. So we can say this times T2 minus 100 degrees Celsius plus 20 kgs of aluminum times 0.973, I guess. Yes, 0.973 times 1000. This is the CP of aluminum times final temperature of aluminum is again T2 minus initial temperature, which is 200 degrees Celsius, is 0. So this is just a simple linear equation with one variable T2. Does anyone want to calculate it? Or I can give the final answer directly as well. I have the solution in front of me. Uh, so if you just simply solve this equation, you will get T2 equals 168 degrees Celsius. If we would have been there in person, I would have made you guys solve it and get to the final answer. Um, but many of you ask for recordings, and so like I have to conduct this session online via Zoom. So, anyways, you guys can solve it later. Simple equation, get the final answer as 168 degrees Celsius. If there's an issue, you can contact me later. Okay. So we are done with the first problem. Now coming to the second problem, which is 1.62. Okay. 1.62. 1.62 states that the inner and outer surfaces of a 5 meter cross 6 meter brick wall with a thickness of 30 centimeters and a thermal conductivity of 0.69 watt per meter degree Celsius are maintained at a temperature of 20 degrees and 5 degrees. Okay. So we we have a wall. This wall is at, let's say, 20 degrees Celsius, and this one is at 5 degrees Celsius, and heat is flowing like this. Okay. How much is this? 0.3 meters, because it says 30 centimeters. And we also have the area of wall. Okay. 5 times 6 meter square, which is 30 meters square. And what else have they given? They have also given the thermal conductivity, K, which is 0.69 watt per meter degree Celsius, or we can also say watt per meter Kelvin. Okay. So these are the things which have been given to us. And what are they asking us to calculate? They want us to determine the rate of heat transfer through the wall in watts. A simple, very simple conduction problem, like a one line answer. So just take like 1 minute and then we'll begin solving it together. Which equation would we be using here? Anyone has any hints? I think it's already week 4 or week 5, I guess, and you guys have gone through this mod, like this specific set of slides in the very beginning of the course. So many of you might have even forgotten what is like covered. So like very simple equations. So let's begin with the solution of this problem. A one line solution. Okay, very simple. So simple, we are going to use the conduction equation in which we'll say, okay, q dot is k times a times delta t over delta x, right? Very simple. They want us to find q dot. What is k? We have k, 0.69. What is a? We have a, 30. What is delta t? Delta t is 20 minus 5, right? 20 degrees minus 5 degrees. which is 15. And what is delta x? Is the difference, this 0.3 meters. Please note that I have converted everything to the SI units. Without this, you might mess up the whole thing, even though the things might be very, very simple. Okay. So just make sure every time you're using the same units in each problem. That way you won't make a mistake. So, like a one line answer, what is Q dot? Q dot is 0.69 times 30 times 15 over 0.3. So, can someone give me the answer? Very simple answer. How many watts? One thing is that two things. If you have a notebook or a pen or like something to write along with, so if we are solving this problem together, then it will stay in your head. But later on, if you're just like looking at me solving the problem and not actually doing it, uh, you will understand everything, but then you're going to forget it very, very quickly. So it won't be of much help, or you might have to go through the recording again, or at least these notes which I'm making. I'll share these, but anyways, why waste your time right now? So okay, anyways, I'll share the answer. The answer is 1035 watts. Okay, very, very simple problem. Yes, thank you. Danish has put it in the chat. Okay. Moving on to the next problem. I mean, this is how I see the PTP sessions. In these sessions, you can just previously, when I was conducting these sessions for the first time, it was for fluid mech, and I started discussing the theory in a lot detail, and then the student said, "Oh no, we don't want that." I mean, nobody wanted to hear the lectures and understanding the concepts. What uh, they are looking for is solving the problems and at least getting the marks in the exams. So for that, you need to like get your hands dirty and solve all the problems. That is why I came. So the second time when I took PTP, it was heat transfer. And that is when I decided, okay, I'm not going to discuss theory much. It is going to be just some good questions from a good reference book. So that is where during my bachelor's, I referred to this book, and it has very good problems, and that is where I am bringing in the problem. Yeah, that's it. Okay, next problem. Problem 1-102. Okay, 1-102 says that a 1.4 meter long, 0.2 centimeter diameter electrical wire extends across a room that is maintained at a temperature of 20 degrees Celsius. Acha, okay. So there is a wire. What is the diameter? It is um 0.2 centimeters, which is, I'm going to say 0.002 meters. Everything I want to keep in SI units. And 1.4 meters long. This is 1.4 meters. And this room, so there is a room in which this wire is kept, and this room is maintained at a temperature of, I'm going to say, T infinity is 20 degrees Celsius. Okay. What else is given? Heat is generated in the wire due to resistance heating, and the surface temperature of the wire is 240 degrees Celsius during steady operation. So the temperature here, Ts, is 240 degrees Celsius. Okay. Uh, then we have two things. In this, the voltage drop is 110 volt and the current is 3 ampere. ठीक है? So, and the problem says that you have to disregard any heat transfer by radiation. So determine the convection heat transfer coefficient for the heat transfer between the outer surface of the wire and the air in the room. So there is like air here, this everything is covered by air, right? So there is going to be convective heat transfer taking place between the surface of this wire, surface, I want to use this color. Okay, the surface of this wire and the air, right? Now we what they want us to calculate is determine the heat transfer coefficient. Going back to the convection very quickly. Um, this is the convection equation, right? Q dot convection is H times A times delta T. So we'll just plug in the equation directly, very simple. Convection problem. So bring in the convection equation and directly put it. Q dot is H times A times delta T. Very simple. What is Q dot? How do we get Q dot? Do we know Q dot? First of all, okay, let's identify what they are asking us to calculate. They want us to calculate H. Okay. So essentially, we need this, we need this, we need this. All these three things. Q dot, A, and delta T. Now, what is Q dot? Q dot we can get from the resistance heating which is happening in the wire. From where the heat is getting generated. It is generating by the resistance heating of the wire. So essentially Q dot is A times V. Okay, I'll write it here again. A times V is Q dot, right? Any wire which is being heated, how much energy does it produce? A times V over T. So uh, Q dot is um, 110 times 3, which is 330 watt, right? What is A? How do we get A? A of outer. I'm going to say AO because from where is the heat transfer taking place? It is taking place from the outer surface of the wire, right? Convection is happening, not conduction. So, how much is the outermost area of this wire? You'll have to think a bit. How much is this area? It is essentially the circumferential area of the cylinder, right? The curved surface area of the cylinder, which is pi times d times L, right? I mean, this whole curved area is going to read like convect heat from itself. So it is pi times what is the diameter? It is 0.002 times what is the length? It is 1.4 meters. So we have this. Okay. Um, okay, just a quick question. Does anyone know why do they usually only give the diameters of the wires or like cylinders and not the radius? Because usually the equations which we have learned from like very childhood are the like for example, what is the area of a circle? It's like pi times r square, right? We never read pi times d square over 4. But usually in all the problems they give the diameter and not the radius. Why is that? That is essentially because they experimentally determine the diameter of the wire. They use vernier calipers. And what does a vernier caliper give you? It gives you the diameter and not the radius. Because that is how you're going to grip the cylinder, right? A jaw here and a jaw here. So this is going to give you the diameter and not the radius. So that is why problems usually train you for the experimental setup and not the like the general way you have learned the formulas. Anyways, that was a side quest. The area outer is the value which I have is 0.009 meter square, 0.009 meter square. And what is delta T? The temperature difference, which is Ts minus T infinity, right? Which is 240 minus 20, which is 220. Problem becomes very, very simple. 330, everything is SI units, so we do not have to care about the units, is H times 0.009 times 220. So what is H? From this, you can very simply calculate H, right? Which is the heat transfer coefficient, which the problem wants us to calculate. H is the value which I have, you can calculate it later. 170.5 watt per meter square Kelvin. Or you can use watt per meter square degree Celsius. Be very careful of the units. This is where you guys are going to make mistakes. Okay. You will solve everything nicely, but at the end you will forget, oh, what is the unit of heat transfer coefficient? I mean, you guys are grown up enough to very simply calculate it using dimensional analysis as well, which is you can say, okay, 330 is what? This is meter square. This is degree Celsius. So what is H unit? H has the unit watt over meter square degree Celsius. Very good. This is correct. But you must also remember sometimes what is the unit of H, or let's say K, the thermal conductivity, which is watt per meter degree Celsius. Uh, this is what is going to save you guys time during the exams. I don't want you guys to do it this way that you are dividing watt over meter square degree Celsius. You must know it. Okay. Okay. Moving on to the next problem. I hope it's clear to everyone. If there are any doubts, you can always put it in the chat, or like even later on, you can discuss with me over Teams or even in person if you want. Hmm. Moving to the next problem, which is from week 2. Can we have a new page? Yes. So we have problem 2.64. I want to use black ink. Consider a large plain ball of thickness 0. 0.3 and thermal conductivity is 2.5 watt per meter degree Celsius and a surface area of 12 meters square. Okay, everything is given. L is 0. 0.3 meters. Thermal conductivity K is 2.5 watt per meter degree Celsius. And surface area A naught is 12 meters square. I usually prefer using A naught rather than just A because A can mean many things. So the left side, okay, let's draw the wall, I think. Okay. The left side of the wall at x equal to 0. So this point is x equal to 0 and x is increasing like this. Okay. At x equal to 0 is subjected to a net heat flux of q dot naught equals 700 watt per meter square. So there is heat coming. It is getting heated. How much? Q dot naught equals 700 watt per meter square. Okay. And the temperature at that surface is measured to be 80 degrees Celsius. So the temperature here, T equals 80 degrees Celsius. This is a tricky problem. Please be careful. I mean, not very tricky, but you must know the concepts to solve this problem. I did not cover this concept during my recap of the week 1 and week 2. So I think I'll be covering that right now during this problem. Um, it is saying assuming constant thermal conductivity and no heat generation. So no heat generation in the wall, express the differential equation and the boundary conditions for steady one-dimensional heat conduction through the wall. Okay, steady one-dimensional heat conduction through the wall. What are the assumptions they are giving us? First thing, assume steady state, right? They want us to assume steady state. So temporal term vanishes, right? What next? They are asking us assume no heat generation. Okay, good. Assume no heat generation. So the q dot term is also 0. Now they want us to express the differential equation and the boundary conditions for steady one-dimensional heat conduction through the wall. They're assuming 1D heat transfer, right? Third thing is assume 1D heat transfer. So, anyone wants to like share how do we begin solving this problem? Which equation to begin with? Anyone has any idea? Where do we begin with solving this problem? Okay, which problem is this? Is it conduction? Is it convection? Is it radiation? Which one is it? It says there is a large plane wall. So plane wall means it is a conduction equation. Yes, we'll begin with the Fourier's law for conduction. Correct. Correct. Yes. So Fourier's law for conduction, and they're asking us go for 2D, go for 1D case. Okay. So 1D Fourier for conduction. What is the equation? It is d square t over dx square equals 0, right? If it would have been 3D, we would have had terms like plus d square t over dy square plus d square t over dz square, right? But right now we don't have that. So it's okay, it's good. Where is the eraser? Okay. Coming back to my black ink. Okay. So this is the equation which we are going to use, right? Very simple equation. D square t over dx square is 0. I want this diagram as well here. So I'll draw it again. Here we have Q dot equals 700 and temperature equals 80 degrees Celsius. Watt, right? Watt per meter square. So we'll start with integrating this equation, okay? So we can say integration of d square t over dx square equals 0. Integration. So we can say dt over dx is some constant, let's say c1, right? Now again integrating. We are again going to integrate this and this over x. So we can say t equals c1x plus c2. I hope all this is making sense to you. This is just simple integration which we are doing, and during integration we get constants every time, right? C1, C2, During differentiation, these constants vanish, but during integration, they come up again. So this is essentially the distribution of temperature inside this wall, which is the third part of this question, but we got it right now. Let's forget it. Okay. We don't need it as of now. What is the question asking us? It says express the differential equation and the boundary conditions for steady state one-dimensional heat conduction through the wall. They are asking for the differential equation and the boundary conditions. So differential equation is this. This is the differential equation. This one. Differential equation. This is the one. That's the solution for the first part of the A part of this problem. Now they also want us to put the um, what is there? The boundary conditions. Okay. So boundary conditions in equation form. Very, very simple, right? How? There are two boundary conditions which are given. This is the first one, this is the second one. But how do we express these in equation form? Let's begin with this one, okay? Let's call this one, let's call this two. So the first one is essentially again the heat conduction equation, which is q dot equals minus ka dt over dx, right? This is the simple heat conduction equation. In this, what do we know? We know q dot. Do we know k? I think we know, right? Yes, we know k, we know a, we just don't know dt over dx. So we can say 700 equals minus times what is k? K is 2.5. 2.5 times what is a? Do we have a as well? A is 12 meter square. So 12 times dt over dx, and everywhere we are using SI units. So we can say simply the first boundary condition is dt over dx equals minus 700 over 2.5 times 12. You can calculate and put this value whatever it comes, and that essentially becomes your first boundary condition, whatever it is. Let's say a. Okay, so dt over dx is capital A. This is the first boundary condition. I don't have the answer to this right now. I haven't calculated this. But this is like very simple. Now coming to the second boundary condition. What is given? This is the second one, right? T equals 80 degrees Celsius. How do we express this? Just directly, we just need to write this, the Dirichlet boundary condition, which is T at x equal to 0 is equal to 80 degrees Celsius. This is all. This is what they are asking for. Okay. So we have just expressed the boundary conditions and the differential equation. Part A is done. Part B, they are saying obtain a relation for the variation of temperature in the wall by solving the differential equation. Okay, they want us to solve the differential equation. Okay. What we already solved it. We got T equals C1x plus C2. Now we have to use these two boundary conditions, this one, and somehow get the values of C1 and C2. How can we do it? Okay, for that, I think we need this value. Can someone just give me the answer to this? Minus 700 over 2.5 times 12. Yes, correct. Okay. Minus 23.333. Okay. So we have dt over dx equals minus 23.33. This is Kelvin per meter. And then we have t at x equal to 0 as 80 degrees Celsius. So first use this one. Let's first use this one, okay? Using this, putting x equal to 0, 80 equals C1 times 0 plus C2. Okay. So we get C2 equals 80 degrees Celsius. We have C2. Okay. We have C2 right now. But how do you get C1? For that, you need to use this thing. dt over dx is C1. dt over dx is C1. Right? So very simply, we can just say this is what dt over dx is, right? Minus 23.33. So we just got C1 equals minus 23.33 Kelvin per meter. Okay, so now we have C1 and C2. We can simply say the temperature distribution inside the wall is minus 23.33 times x plus 80. Okay, this is how we get it. Now this is the second part, the B part for the problem is done. Now coming to the C part. In the C part, they are asking us evaluate the temperature of the right surface of the wall at x equal to L. Yeah, so this is x equal to 0 and this is x equal to L. And how much is this length? Okay, how much is, okay, they have given the length as 0.3 meters. So this one is 0.3, okay. And they want us to calculate the temperature at x equal to L. What is the temperature here? So simply we have the temperature equation, right? We just simply have to plug in here x as 0.3. Can someone again do it and tell me the final answer? T equals minus 23.33 times 0.3 plus 80. What is the final answer? 73 is what Joey is getting. Danish, you wanna put in a value in the chat? Yeah, okay, 73.001. Okay, whatever. It's fine. Minus 23.33 times 0.3 plus 80. Yes, 73.001 degrees Celsius. Yep, so we are done with the second problem. The third one I was planning to leave for you guys to do. Okay, do we have it? Yes, we do have it. 2.82. Nuclear reactor, 1 centimeter diameter, uranium rods. I'm not reading it. It's a hard problem. You guys, it's up to you guys to solve. Okay. I mean, I had already planned that I'm going to leave this problem to you guys, and just in case you face a problem solving it, uh, you can ping me and we can discuss maybe in the next week's session or sometime later. That is all for today, which I had for you guys. If anyone wants to ask anything or share anything, put in the chat or unmute yourself and speak or whatever works for you. If not, I will end this meeting in 1 minute. Oh, we covered everything in like 1 hour exactly. Yes, thank you very much for attending. I really become very happy when like people come to the PDB sessions and attend. So I try to give like whatever best you guys can have from this short 1 hour or like 2 hours sometimes. I've taken it for 3 hours as well, but then it's like too much. So I try to finish early. Okay, that is it. Thank you very much for joining and see you guys later next week. Bye bye. I'll end the meeting now.